Welcome to Tell Me More Stories Told His podcast.
Hey everyone.
Get ready, because today we're diving deep, like
Mhm.
really deep, into the world of artificial intelligence.
Yeah, we're going on a bit of an adventure, you could say. Uncovering the story behind a technology that, well, it's pretty much everywhere now.
Exactly. We're talking about the foundation for a lot of the AI. You hear about those chatbots, the amazing image generators, all that stuff.
And it all comes back to this one research paper. Sounds kind of dry, maybe.
Huh, maybe the title does. But trust us, the story behind it. Anything but dry. It's actually fascinating.
It really is. It's got context, brilliant ideas, a quirky backstory, even a connection to a super famous band.
Okay, let's not give that away just yet.
Yeah.
But yeah, our mission today is to unpack all of that. So let's get into it.
All right. So the story starts in 2017. There's this research paper published by 8 scientists, mostly from Google Brain at the time.
And the title.
Attention is all you need.
Simple. Almost sounds like a self-help mantra or something.
Maybe. But don't let that fool you. This paper, it was like a lightning strike in the AI community. It introduced what we now call the transformer architecture.
And that architecture is basically the engine behind most modern large language models, right?
Precisely. It's foundational. But, okay, rewind a bit. What problem were they actually trying to solve back in 2017?
Good question. What was the big hurdle they were up against?
The main focus, initially anyway, was machine translation. Getting computers to translate text from, say, English to German accurately and fluently.
Okay, and what were the tools they had for that back then?
The dominant tech was called seq sequence to sequence. Often this used things called recurrent neural networks, or RNNs.
RNNs. I remember those. They process information step by step in a sequence.
Exactly. And a more advanced version called LSTMs, long short-term memory networks. They were better, but still sequential, word after word after word.
So what was the drawback if you're translating a long document or maybe a whole conversation?
Well, think about trying to remember the exact beginning of a long speech by the time you get to the end. It's tough.
Yeah, you lose the details or the nuance.
Kind of like that. RNNs and LSTMs, they struggled with these long-range dependencies. The meaning from the start of a sentence could get kind of fuzzy by the end.
The context gets lost.
Right. And this sequential processing, it also created a bottleneck. You couldn't easily speed things up just by throwing more computer power at it because step 2 had to wait for step 1. No real parallel processing.
Okay, so they needed something faster, something that could handle longer texts better, grasp the whole picture at once, maybe?
You got it. And that's where this idea of attention really comes into its own. It's the core innovation in attention is all you need.
The transformer architecture.
Yep. Based almost entirely on this attention mechanism. Now, attention wasn't totally new. People had been experimenting with it, but this paper took it in a radical new direction. They basically said, what if we only use attention? No recurrence at all.
Okay, so dive into that. What is this attention mechanism and how do they use it differently?
Right, so imagine you're reading a sentence. You don't weigh every word equally, do you?
No. Some words are more important for the meaning. Keywords, maybe.
Exactly. Your brain attends to the crucial parts. The attention mechanism lets the AI model do something similar. When it looks at one word, it can simultaneously look at all the other words in the sentence and figure out which ones are most relevant for understanding that specific word in context.
That sounds much more powerful and faster if it's simultaneous.
Way faster. And it gets how words relate to each other, even if they're far apart in the sentence. No more just relying on the immediately preceding words.
How does it work under the hood? I read something about Q, K, and V.
Yes. Query, key, and value matrices. It's a core part of what they called scaled dot product attention. Think of it like this. For each word, the model generates 3 representations.
Query, key, value.
Right. The query is like asking a question, what information do I need? The keys are like labels for all the words, saying, here's the kind of information I have. And the values are the actual information content of those words.
Okay.
The model compares the query of one word with the keys of all the other words. If a key is a good match for the query, it means that word is relevant.
And then it pulls the value.
Exactly. The model calculates a score, the attention weight, based on the query key match, and uses that score to weigh the importance of each word's value. So it creates a new representation for the word that's blended from its own information, plus relevant information from all the other words it's paying attention to.
Wow. Okay, so every word is constantly looking at every other word and asking, how relevant are you to me right now?
That's a great way to put it. And critically, all these calculations can happen at the same time, in parallel, no more sequential bottleneck.
That's the key to the speed up.
A huge part of it, yeah.
Then there was multi-head attention. What's that about? Sounds like making it even more complex.
It does, but it's actually really clever. Instead of calculating attention just once, multi-head attention does it multiple times in parallel, each with slightly different learned query, key, and value sets.
So like looking at the sentence from different perspectives simultaneously.
Exactly. Think of it as having multiple attention heads. One head might focus on, say, grammatical relationships, subject-verb agreement, that kind of thing.
Okay.
Another head might focus on semantic relationships, words that mean similar things, or opposites. Another might track pronouns and what they refer back to.
Ah, so it captures different types of connections between words.
Precisely. It gives the model a much richer, more nuanced understanding of the language, all happening in parallel. It's not just faster, it's deeper.
That's brilliant. But wait, if it's processing everything at once, how does it know the order of the words? Dog bites man is very different from man bites dog.
Excellent point. That was a crucial problem to solve. Since the core attention mechanism doesn't care about sequence, they needed to explicitly add information about word position.
How'd they do that?
They introduced something called positional encoding. Basically, they created a unique mathematical signature for each position in the sentence. First word, second word, third word, and so on.
A signature, like a fingerprint for the position.
Sort of. They used sine and cosine functions of different frequencies. It sounds a bit weird, maybe.
Sine and cosine from trigonometry. Why those?
Yeah, it was quite elegant. The idea was that these wave functions have properties that make it easy for the model to learn relative positions. Like, it could learn how far apart words are. And importantly, they theorized it might help the model generalize to sentences longer than any it saw during training.
Because the pattern of sines and cosines can just keep going.
That was the hope, yeah. So they add this positional signature directly to the representation of each word before it goes into the attention layers. So the model gets both the word's meaning and its position.
Okay, that makes sense. So before the Transformer stormed onto the scene in 2017, you mentioned RNNs and LSTMs were king. Let's trace that path a bit.
Sure. So for years, RNNs were the standard for sequence tasks. But they had this issue called the vanishing gradient problem.
Vanishing gradient. Sounds like the signal fading away.
Pretty much. When training, the error signal used for learning would get weaker and weaker as it propagated back through time in a long sequence. So the network struggled to learn connections between words that were far apart.
Made learning long-term dependencies really hard.
Exactly. Then came LSTMs. They were specifically designed with internal gates to control the flow of information, allowing them to remember things for much longer and overcome that vanishing gradient issue mostly.
So LSTMs were a big step up.
Oh, huge. They became the workhorse for machine translation, speech recognition, all sorts of sequence stuff, but still sequential.
Right, still processing step by step. And you mentioned attention wasn't totally new.
Correct. Around 2014, researchers started adding attention mechanisms to existing C2-sec models, often built with RNNs or LSTMs.
Why? What problem did that solve?
The original Seq2-sec models had a bottleneck. They tried to compress the entire meaning of the input sentence into one single fixed-size vector, like summarizing a whole book in one sentence.
Sounds difficult, especially for long sentences.
Very. So attention was added to let the decoder part, the part generating the translation, look back at all the words in the input sentence at each step. It could then focus or attend to the most relevant input words when generating the current output word.
Ah, so it didn't rely solely on that compressed summary. It could peek back at the source.
Exactly. And it gave much better results, especially for longer sentences. But again, it was still layered on top of a sequential RNN LSTM structure. It helped, but didn't solve the parallelization problem.
So the bottleneck was still there, just maybe eased a bit.
Right. Then some interesting work came out, like in 2016, on decomposable attention. It suggested you could get really good results on language understanding tasks using just attention and simpler feed-forward networks, which are parallelizable.
A hint that maybe the recurrence wasn't strictly necessary?
A strong hint. One of the researchers involved, Jacob Uskereit, who later co-authored the Transformer paper, apparently suspected even then that attention alone might be enough for translation, which was pretty radical.
Okay, so the stage was set. The limitations of RNNs were clear. Attention was showing promise. Then boom, 2017. Attention is all you need.
Boom is right. The paper drops this full encoder-decoder transformer model, no recurrence, just stacked layers of self-attention and those feed-forward networks.
And the goal was explicitly to break that sequential dependency for better translation.
Yes. Enable parallel processing, train faster, handle long dependencies better, and hopefully get state-of-the-art results. And that multi-head attention was really key to making the parallel attention powerful enough.
And this is where the fun facts come in, the title.
Ah!
Yes, attention is all you need. A direct nod to the Beatles. All you need is love.
I love that. Injecting a bit of pop culture into a dense research paper.
Totally. It was playful, maybe a bit provocative, and the name Transformer itself.
Apparently, Jakob Uskerate, just like the word, no deep technical meaning behind the name choice itself.
That's amazing. Just sounds cool.
Pretty much. And it gets better. The internal team working on it called themselves Team Transformer.
Seriously.
Yep. And an early design document was supposedly titled Transformers, Iterative Self-Attention and Processing for Various Tasks, and even had a drawing of Transformers characters like the robots.
No way! Optimus Prime explaining self-attention. That's hilarious.
Right. Shows they had a sense of humor about it, but they were serious about its potential. They didn't just test it on translation.
What else did they try?
Early on, they did English to German translation, obviously, but they also got it to generate Wikipedia-style articles about the Transformer.
Meta.
Super meta. And they used it for sentence parsing, too. These early experiments convinced them it wasn't just a translation machine, but a more general-purpose language understanding architecture.
And boy, were they right. The impact since 2017. It's been staggering, hasn't it?
Understatement of the year. As of, 2025. That paper has been cited over 173,000 times.
Wow. 173,000. That's astronomical for a research paper.
It puts it right up there among the most influential scientific papers of the 21st century across all fields. It truly kick-started the modern AI boom we're living through.
So it became the blueprint.
The absolute foundation for so much generative AI. Google's own BERT model came shortly after. Then you have the whole lineage of OpenAI's GPT models.
Including ChatGPT, which everyone knows now.
Yep. And it wasn't just text. Vision transformers, or VITs, adapted the architecture for image understanding. It's used in speech recognition in multimodal models that handle text and images.
So when we see things like DALL-E, Stable Diffusion, even the new video generator Sora, the transformer is under the hood there too.
In various forms, absolutely. Its ability to model complex relationships in context within vast data sets is what makes a lot of that possible. It translates the attention concept to pixels or relationships between frames in a video.
Mind-blowing. From improving translation to generating photorealistic images and video, all stemming from that one core idea. Who are the people? The 8 authors.
Right, the ED co-authors. Ashish Vaswani, Noman Shazir, Nikki Parmar, Jakob Uskerate, Lion Jones, Aidan Gomez, Lukas Kaiser, and Ilya Polasukin.
Quite a team.
A really diverse team, actually, in terms of origins. And they made a point of listing the authors randomly, emphasizing that it was a truly equal collaboration, no single lead.
That's a great way to acknowledge teamwork. What happened to them after this huge success? Did they stick together at Google?
Interestingly, no. Over time, all 8 eventually left Google.
All of them. Wow.
Yeah. They went on to found their own AI startups or join other ventures. People like Noam Shazir co-founded Character.ai, Ilya Polasukin co-founded Near Protocol, Aidan Gomez co-founded Cohere. They wanted to keep pushing boundaries, maybe in ways they felt they couldn't within a larger structure.
Fascinating. The pioneers moving on to build the next things. What about the nuts and bolts of training those first models? What kind of data do they use?
For the translation tasks in the paper, they used standard benchmark datasets. The WMT 2014 English to German dataset, which had about 4.5 million sentence pairs.
Okay, that's a lot.
And an even bigger English to French dataset with around 36 million sentence pairs.
Whoa. And the computers needed?
They trained on NVIDIA P100 GPUs, 8 of them, I think. The base model trained for about half a day.
Only half a day? That seems surprisingly fast for the time.
Right. And the bigger models took around 3.5 days. But here's the kicker. The total computational cost, the amount of processing power needed, was significantly less than the previous state-of-the-art models they were comparing against.
So it was faster and more efficient to train.
Exactly. While getting better results, that parallelization really paid off.
Any special tricks they used during training?
They used a few important techniques. A specific learning rate schedule, starting small, increasing it, then letting it decay. They used dropout, which is a standard way to prevent the model from just memorizing the training data. And something called label smoothing. which slightly softens the target labels, and they found it actually helped improve accuracy and the final translation quality score, the BLEU score.
Got it. Lots of careful engineering went into it, alongside the big architectural idea. If you're finding this journey into AI's building blocks as cool as we are, definitely hit that subscribe button. You won't want to miss the other stories we uncover here on Tell Me More Stories Told as podcast.
Seriously, do it.
Okay, so bringing this all together, what's the big picture for someone listening? What does this story mean for, us?
Well, I think the main thing is that this shift, this move towards attention and parallel processing pioneered by the transformer, it fundamentally changed what AI could do. It unlocked a new level of sophistication.
It moved AI from being okay at specific tasks to being, well, surprisingly capable across many domains.
Exactly. That ability to process information in parallel, to weigh connections across vast amounts of data. It's why we now have AI that can translate languages pretty much instantly, generate stunningly creative images from text prompts, and hold conversations that feel remarkably human-like.
The ripple effects are just undeniable. You see it everywhere.
Absolutely. The tools you use, the services you interact with online,
Yeah.
many of them have transformer DNA inside them now. It all traces back to that 2017 paper with the catchy title.
It really is an incredible story of innovation.
It is. And here's something to chew on, maybe a final thought for you listening. The transformer has been incredibly dominant.
For sure. The last, 7, 8 years?
Yeah. But the original authors, as we said, they've moved on. They're actively working on what comes next, which suggests even they believe the transformer isn't the final word.
So the revolution continues.
Always. So the question becomes, what is the next fundamental breakthrough going to look like? What replaces or evolves beyond the transformer? And who's going to be the team to figure it out?
That is a great question. Maybe a story for a future deep dive, indeed.
Could be.
Well, this has been absolutely fascinating. Thanks for walking us through the story of the transformer.
My pleasure. It's a great story to tell.
And thanks to all of you for joining us on this deep dive on Tell Me More Stories Told as podcast. We'll catch you next time.